Okay, hello everyone. Happy to be here giving the first talk, 15-minute talk at least. So I'm going to talk about benchmarking human AI decision making using decision theory. And this works in collaboration with Xiang, who is here today. He's my PhD student. He'll be doing a short talk tomorrow, and he's a lead author on everything I'll present, so please talk to him, as well as Yifan and Jason, my colleagues. So the goal of using AI to augment intelligence often assumes that we'll get complementarity, or sort of better performance than we would get from either agent alone if we put these two together. So we want the best of both worlds. But we often see in practice that AI-assisted humans making decisions underperform the AI alone. And we see this across different domains, medicine, finance, law, etc. And when we see results like this, it motivates this kind of breathless rush to develop better interfaces, things like better AI explanations, thinking that we're going to help the human sort of get more out of the AI. But one of the problems that's been motivating my group recently is that often when we study human AI decision making and try to design for it, the performance targets themselves are ambiguous. So we might see a result like this, but one of the things we don't really know is sort of how bad is this? Like, how well could we have expected this human and AI to perform together? Was there a lot of room for complementarity? And similarly, even when we see a result like this, where the human AI team outperforms the better of the two agents alone, we still don't know sort of how well they're doing relative to how well they could do. So, are they almost all the way there in terms of getting the best possible performance, given what we know about the information in the human judgments and the AI judgments? Or is there still a long way to go? And so we need to know this in order to know things like how much more effort should we invest in improving the interface or the explanations or the workflow to get better decision making from the pair. And one of the issues that occurs a lot when we're studying this human AI decision problem is that the measurements that are often used set up sort of performance targets that cannot be attained in practice. So often authors or researchers will use things like post hoc accuracy as sort of the measure of appropriate reliance on an AI, meaning that the human's expected to agree with the AI whenever it's right and disagree whenever it's wrong. But statistically, this is a bit incoherent because it doesn't take into account the actual information available at the time of the decision. So often 100% post hoc accuracy is just not possible. And so what we want to do is define appropriate reliance and complementarity in a way that does take into account the available information, and do that by thinking about what is the best attainable decision performance given some decision problem that we're studying human AI decision making on. And so, our goal is to be able to take some evaluation distribution, so some distribution that we want to evaluate the human AI team on. And we want to be able to first attain what is the best possible performance on this decision problem given a pairing of a human and an AI. And then we also want to be able to look at, how much better is that performance compared to the better of the two agents in isolation to sort of measure this sort of maximum possible value of putting the two agents together over just having the better of the two alone. Once we've defined that value, we can observe the human and the AI, making decisions together. And we might see some loss relative to this best attainable benchmark. And we might want to understand what are different reasons that that loss occurred. And so we're also going to try to decompose these sources of loss in the observed performance relative to the benchmark. Okay, so I'm going to assume a standard workflow in which the human views some decision instance. I'm going to use diagnosis as an example. So imagine we have a doctor, they view some patient, information, maybe some images. They're going to make their own independent prediction. We usually assume that the human can do that. Then they're going to view an AI prediction or have access to this, and then they're going to make a final decision. And what we'll note is that there's a couple different problems happening in this relatively simple workflow. So we have a prediction problem where the human and the AI are both making predictions, but we also have a decision problem where the same human is then deciding to go with their own judgment or the AI. What we want to do is construct a benchmark to help us understand the best attainable performance for the decision. But first, let's formalize these two problems and then focus on this decision problem. So these are kind of two related problems. So for diagnosis, as an example, the prediction problem, we could say the payoff relevant state here that we're trying to predict is the true condition of the patient. The action space, or the output space for the predictions, whether they're from the human or the AI, is also going to be, the same as the state space, the predicted condition that the patient has. The two predictors, the AI and the human, we're going to assume have access to some patient feature vector, X. And when we define an evaluation distribution or an evaluation data set, you could say that we are also defining some data generating model. So there is some distribution over the features in the state. This is sort of the distribution that we're evaluating against. And we're going to assume, if we have these agents generating predictions, that there's some scoring rule or loss function, which essentially takes in their choice of action and the ground truth and assigns some score or loss, if you prefer. So that's the prediction problem. What we want to do is benchmark performance on the decision problem. And this is a related problem, but not quite the same. So let's talk about how we model or formalize the decision problem. So again, our state includes the ground truth condition of the patient, but we're also going to say that the state includes the AI and the human predictions, because we care about the sort of correlations between all three of these. The action space that the decision maker faces is now whether to go with the AI prediction or the human prediction. And the signal they have access to includes the patient features, again, the information, but also the human prediction, the AI prediction. Maybe there's also some explanation of the AI prediction, and this is what the decision maker is sort of using. The data generating model is again going to include the joint distribution over the features and the ground truth state. But now we also care about this distribution over the human predictions and the AI predictions. So you can think of it as one big joint distribution, which is defined by our evaluation data set. And again, we have a scoring rule. And here we're just going to use the prediction scoring rule, but we're going to apply it according to whether the choice of action was either the AI prediction or the human prediction. Okay, so this is our decision problem formalization. And now what we want to do is focus on this decision problem, and we want to try to solve it. So we want to ask, what is the best possible performance that any decision maker could get on this problem, which we formalized in decision theory? Oh no, I knew my slides would be off somehow. So yeah, try and imagine shifting those colored boxes at the top over. We're trying to think about what's the best possible decision that any decision maker could make between the human and the AI prediction. And to do that, we're going to think about what would the idealized Bayesian rational agent do. So this is going to be a decision maker who's going to update according to their beliefs, according to Bayes' rule, and is going to choose the utility maximizing action. So, we can think about the process by which they encounter these decision instances and make their decision. So we're going to assume that they start with prior beliefs. So essentially, they go into this knowing the prior probability that the human versus the AI is correct on this evaluation distribution. They're then going to, on any given decision instance or patient, see the signal, which includes, again, the features, the AI prediction, the human prediction, maybe some explanation, and they're going to update to Bayesian posterior beliefs. And you might wonder sort of how are they updating? Well, we're going to assume that they are sort of maximally informed as any participant, could hope to be. So we're going to assume not that they know the ground truth on every single instance, but that they know this joint distribution over the state and the features and the AI and the human predictions. So they're going to use that information they have about that probability distribution to update to their posterior beliefs. And then on every decision instance, they are going to choose the utility maximizing action. So this is going to sort of define the best possible performance on this decision problem. We do this over our evaluation distribution or our evaluation data set, and this allows us to create what we'll call this rational agent benchmark. This is the expected score of the rational agent who's choosing the score maximizing action after updating to the Bayesian posterior. And so the distance then, or the difference between this benchmark and what we're going to call the baseline, the expected score of the rational agent if we only constrain them to using the prior, meaning they only go on each instance with either the human or the AI, because whichever one is better, or they're sort of using a fixed strategy, that difference becomes our value of complementation. And this measures essentially how much extra boost in performance do we get when we bring in the additional agent. So, how do we use this? Well, let's imagine first we want to deploy an AI, but we don't know, how much it might help. And so let's imagine we can query the humans for their predictions on some set of instances. We can query the AI, Something we might want to look at is, how big is this value of complementation before we even deploy the AI? So is there room for performance to go up on this task when we bring in the other agent? And specifically, we want this value of complementation to be large relative to the baseline score. This means there's actually some boost from combining these agents. After we deploy the AI, we might, observe performance. So we now know the actions that were chosen. The human actually made decisions between the AI and the human prediction. And now we might want to understand, why are they not achieving this benchmark? So we see some loss, and so we might want to understand why. And so we can imagine two different types of errors that a human could make relative to the relative to the rational agent. So one type of error is that the human might over or under rely. So they're relying at the wrong rate overall. We'll call that reliance loss. Another type of error might be that they don't know exactly when it's in their best interest to rely on the AI. So maybe they're relying the right amount of the time, but they're differing from the rational agent in terms of which instances they're relying on the AI. So the rational agent is always going to go with the AI in the cases where the expected difference in payoff of going with the AI versus the human is biggest. And so there might be a sorting error. So we'll call that discrimination loss. In order to tease these apart, we're first going to remember that this benchmark is going to define the optimal reliance rate. The rational agent will rely optimally on the AI. What we can do to sort of differentiate reliance loss is now define a second benchmark, which we'll call the misreliant rational agent benchmark, where here we're going to have the rational agent, make decisions on this evaluation distribution, but we're going to force them to rely at the same rate that the human relied. And so essentially the rational agent is going to fix the discrimination errors that the human made, but still rely at the same rate. And so now the difference between the benchmark and this misreliant rational agent is going to be our reliance loss. So this is the loss in performance due to the human over or under relying overall. And the remainder, the difference between this misreliant benchmark and the human AI observed performance, is discrimination loss. So this is, the errors because the human didn't rely in the cases where it was sort of most in their best interest. So to sort of summarize this first piece of, or this first framework I've discussed, we're essentially arguing that if we want to understand how to design better human AI collaborations and evaluate things like appropriate reliance, we need to understand the decision problems that we are inducing whenever we choose some evaluation distribution and study a decision task. And specifically, we want to, calculate performance benchmarks and then compare. And so here we're using this notion of a Bayesian rational agent. So we might also wonder, could we apply a similar approach, this decision theoretic kind of framework, to learn now about the value of different specific interfaces that we might give the human who's making decisions with an AI. So we might ask, could we quantify the value of an explanation technique to some decision problem, just like we quantified the value of the additional agent's decisions? And so in a recent paper, we argue that, whenever someone's proposing a new explanation technique for an AI model, they should be able to name at least one decision problem where they expect the performance to improve when they offer access to that explanation. And so there's a few ways to think about this. So first, let's assume an explanation which is a function of the features and the AI prediction. This is, many explanations that are popular, Lime, SHAP, et cetera, are simply functions of the AI prediction and the features. And so we might ask, with such an explanation, what's the theoretic value of this explanation? Like, how much does, the best possible decision maker benefit when we give them access to this explanation versus take it away? So imagine we have a benchmark here. This is the rational agent with the full signal, including the explanation. And we might ask, what happens if we just remove this explanation component? Yeah. And what's interesting is to the rational agent, an explanation has no value, because an explanation is just a function of information they already have, the features and the AI prediction. And so we would get the same benchmark if we did this. And in fact, we would get the same benchmark if we took away the AI prediction as well from the rational agent, because that too is a garbling of the features and the state. And so essentially, the rational agent's benchmark is going to be the same with all of this information versus with only the features. Like, that's the power for them. And so doing this, at first, we make a simple observation, which is, well, the rational agent never benefits from explanations. This Bayesian utility maximizing agent will never benefit. And so this kind of tells us that when we're using explanations, we are implicitly assuming that humans are either, not as well informed as sort of this rational agent, or they are irrational in terms of their use of information. And so, we can think about the value of explanation here as helping the humans unlock information that's already there in the features or the AI prediction. And so if we want to understand the sort of value of an explanation, we can look and compare the human performance to the rational agent with the features alone. So this is sort of the upper bound on human performance with the explanation. And so, I don't have time to go in great depth, but I'll just briefly summarize. In this paper, we're basically proposing a theoretically grounded workflow for explainable AI, where first, like I said, we should be able to identify the decision problems where an explanation could help, which means first looking at the theoretic value of explanation. How much does a rational agent benefit from the features? If there's no benefit there, the explanation could not help humans much. We can also look at how much, value does the explanation potentially hold to agents over what information is already encoded in their decisions. So we can also look at, the information encoded in the human predictions and how much complementary value is potentially there by, again, using the rational agent with the features. And finally, we can, observe human performance with and without an explanation. This we call the behavioral value of explanation. And the key idea is we should be interpreting this behavioral value within a framework in which sort of, best possible behavior is well defined. So I will wrap up there. Again, see Ziyang's talk tomorrow and talk to him. He'll talk more about this complementary value piece. And thank you.
We have time for one quick question.
Oh, sure, yeah.
Yeah, sorry, yeah. RT, quick on the draw, and you're also close to me here.
Thank you. Yeah, and sorry for dominating. But does your rational agent assume that the human and the AI are independent?
Yeah, so we are assuming these are independent predictions, yes. Like I said, often, sort of this workflow I showed is sort of the standard assumption where we're generally assuming and many times prompting the human for their prediction before they even see the AI. So it is assumed that these are independent.
Thank you.
Yeah, and it would not be the same if we did not assume that.
Okay,
Great.
thank you. So next up is Justin Weiss, who is a manager and senior research scientist for human-centered AI. And I don't have a fun fact for everyone, but just want everyone to know, this one I do. Justin is a 3-time CMU grad, so welcome back, Justin.
Yeah, thank you so much. That would have been my fun fact. It's amazing to be back here after a very long time. So I wanted to start this talk by saying something that I hope is a little bit provocative, and that there's kind of this chasm that exists between how the AI and machine learning community thinks about producing state-of-the-art models and how the human-centered AI community thinks about evaluating team performance. And what I'm going to try and demonstrate in this talk is that the reason that it's difficult to develop useful AI systems is because we collectively as a community are spending way too much time on the left-hand side over here, worried about state-of-the-art model metrics, and not enough time on the right-hand side over here thinking about evaluating human AI team performance in very comprehensive